Alright, so in this lesson, we're going to take what we've been doing. We've had stoichiometry, and honestly, what that's been doing is determining how much I should get in a reaction. However, in the lab, it doesn't always work out that way. In fact, you guys haven't done it yet, but in the stoichiometry lab we're doing in the other class, we've been trying to collect as much copper of a product as we can, and it's sticking to the size of the beaker. It's sticking to the magnet we're using to stir it, and we're not doing a very good job getting it all. So that stuff happens. You can only hope to get the maximum that you're expecting, but in reality, stuff happens, and you end up losing some of your product in different ways, or maybe you have contaminated chemicals, or maybe the skill of the lab person doing it isn't that great. There's all sorts of factors that could go into why you didn't get what you expected to. So that's our goal. This section is to kind of look at determining the limiting reactant and then using that to find the percent yield. So limiting reactant is the reactant that limits the amount of the other reactant that can combine in the amount that can form in a chemical reaction. So you got to remember we have two things. We have the limiting reactant, then we have something in excess. So one thing kind of prevents me from making any more. One thing is going to be extra or left over. Unless I have the perfect amount, the perfect combination. It's kind of like when you're eating nachos and cheese and you run out of nachos, but you have extra cheese. So you got to go get more nachos, and then you have extra nachos, so then you got to get more cheese until you get that perfect ratio. Or same with like hot dog buns and hot dogs. They sell them the buns in packs of 8, but the hot dogs in packs of 10. What's going to happen? You're not going to be able to make the full amount of hot dogs, right? So let's actually keep on the hot dog analogy there. Let's say you had 8 hot dog buns, but 10 hot dogs. How many hot dogs could you make? Like, how many full hot dogs could you make? If you had 8 buns and 10 hot dogs. I guess I should say, like, you have 8 hot dogs, but how many like full sandwiches could you make of like hot dog sandwiches? Yeah, I'm limited by the number of buns, right? Because I have extra or excess hot dogs. I'm gonna have 2 left over because the buns ended up being what's called my limiting reactant. Probably would have been easier with sandwich slices. Like if I want to make grilled cheese sandwiches and I had 3 pieces of bread, 3 slices of cheese, what do you think my limiting reactant's going to be there? Can I make 2 sandwiches with 3 pieces of bread? Yeah, I could use 2 pieces of bread, but yeah, one would have to be a flatbread, right? So yeah, 3. That's true. We get creative there, but chemicals don't work that way. They're not going to get creative. They're going to just act as if there's a limiting reactant and an excess. So you can see the example here. We had 5 carbon atoms and 10 oxygen molecules. We could make 5 carbon dioxide molecules based on my 5 carbon atoms, but then I'm going to have extra. Once I run out, because it takes 2 oxygens and 1 carbon to build it. I'm going to be able to build 1, 2, 3, 4, 5, but then once I run out, I'm going to have 5 oxygen molecules left over. So you're going to do a lab with that online with sandwiches. Before we do that, we're going to look at some sample problems. So this is where I see the most confusion, I think, is the trickiness of finding the limiting reactant. That's why I was using the hot dog as an example, the grilled cheese. If I have silicon dioxide, it's usually quite reactive, but it will react with hydrogen fluoride, hydrofluoric acid. According to this equation, if I add 6 moles of HF to 4.5 moles of SiO2, which one's the limiting reactant? So, in other words, I have 6 moles of this stuff and 4.5 moles of this stuff. Which one is going to prevent me from making more eventually? Yeah, that's what it's tempting to say, the 4.5, because there's less of it, right? But we have to look at the molar ratio. There's 1 mole of this to 4 moles of this. So thinking of I try to think of something that has 4 to 1 ratio. Like, let's just say the car, you've got 4 wheels for every, like, body, I guess, of the car. I know it's a lot more complicated than that, but let's just say that it's made of the body and 4 wheels. So, in my analogy here, I've got 4.5 car bodies. So 1, it's more like a truck, but 2, 3, 4.5. So I guess just end there. So I've got 4.5 car bodies, and then I've got 6 wheels. So 1, 2, 3, 4, 5, 6. So I want to build a car. I use 1 car body and 4 wheels. That's all good. I made 1 car. Now I go to make the second car. Yeah, I can't do it because I could maybe make the half car, but I'm limited. What's limiting me? Is it the cars or the wheels? Yes, it's the wheel. Thank you. I almost said the cars, but yeah, it's the wheels. So I need 2 more wheels if I want to make another car. So this wheels was my limiting reactant. Car bodies was an excess. So you see how, in this case, it's the same thing. The 4HF, that was my limiting reactant. The SiO2 was in excess then. Does that make a little bit more sense? Because I know it's tempting to say this is limiting, but it's not always the smaller moles. It's the fact that if I have 1 mole of this, I need 4 moles of this. So if I have 4.5 moles of this, I technically need 18 moles for the reaction to work. 6 moles is not enough. So there's the way to do that. Take your 2 numbers divided by each other. So 4.5 or let's actually do 6 divided by 4.5. It's going to give me 1.33 in the calculator. Ask yourself what the actual ratio is 4 to 1. So if this number is bigger than what's actually happening, then that tells me that this is a limiting reactant. If it went the other way, if I had plenty, say I had 26, I'm going to get a number greater than 4. That would then tell me that this is my excess. So if I get a number greater than what it's supposed to be, it's excess. If I get a number less than what it's supposed to be, it's my limiting reactant. So we'll do practice with that on the homework tonight. There's just a few terms I need to introduce you to. There's the theoretical yield, the actual yield, and the percent yield. And a lot of times I see people getting the theoretical and the actual yield mixed up because you would think the actual yield would be like what it actually should be, but that's not the case. The actual yield is what you're getting in the lab. So when I actually do the lab, what do I get? Theoretical yield is when I do the stoichiometry, when I do the math. What should I get? So like taking a test, there's a number of questions you should get right. You should get all 50 questions right. But the actual performance on the test, maybe you only got 38. Exactly. How many? How many did you say? Oh, I thought you said a number. But then to find that, you're going to take the actual number you got divided by theoretically what you should get if you studied. That's going to be your percentage. So just like a test score. And same in lab, if you were supposed to get this much copper, but you only got this much copper, percentage is going to be how much you actually got divided by how much you should have got. So here's my sample problem to drive that home. We've got chlorobenzene, which is C6H5Cl, is used in the production of some important chemicals like aspirin, dyes, and disinfectants. We can react chlorobenzene with chlorine, and we get C6H5Cl, we can react benzene with chlorine, so we get chlorobenzene and hydrochloric acid. So when 36.8 grams of benzene reacts with an excess, so all the chlorine we need, we don't have to determine the limiting reactant here. It just is going to be the C6H6. The actual yield we get is 38.8. So what's the percentage yield of C6H5Cl? So what we have to look at is we have to find out how much we should have gotten. So if I have 38.8 grams of C6H6, can someone find me the molar mass of C6H6? Sounds right, 78.1. So I'm converting it into grams, converting it into moles from grams. Now I have to use my mole ratio to determine what my theoretical yield of chlorobenzene is. So my mole ratio is actually just 1 to 1. So 1 mole of C6H5Cl to 1 mole of C6H6. Now I'm in moles of C6H6, but I want grams. So I'm going to do grams of C6H5Cl to moles of C6H5Cl. And can you give me the molar mass of chlorobenzene, C6? So it'd be like 72 plus 5 plus 35, I think. Yeah, C6H5Cl. 112.5, that sounds right. So moles cross out. So what I'm going to do is I'm going to take 38.8 divided by 78.1 times 1 over 1 times 112.5, and I get 55.9. So what this is this is my theoretical yield. In an ideal lab situation, I should get 55.9 grams out when I put 38.8 grams in. However, what was my actual yield? Yeah, I only got 38.8. So that's like getting 38.8 out of 55.9 on the test. So 38.8 out of 55.9. So 38.8 divided by 5.9. 0.694. So what's that going to translate into as a percentage? 69.4%. So that's my percent yield. We understand the difference between theoretical yield is what you should get, actual yield is what you actually got in the lab, and then percent yield is the actual divided by theoretical. Any questions on that problem? So I'm actually going to jump to number 7 here. So real quick, if a chemical reaction involving substances A and B stops when B is completely used up, what would B be then? Limiting or excess reactant? Did you say limiting? Because B is used up, so it would be our limiting reactant. How about this one? The chemist calculates the maximum amount of product. What's the maximum amount of product that could be obtained? Is that your percentage yield, mole ratio, theoretical yield, or actual yield? Yeah, it is C, theoretical, because actual is what we get when we do the lab. And then finally, the maximum number of moles of AlCl3 that can be produced from 5 moles of Al and 6 moles of Cl2. So let's actually work through this one. So I need Al to Cl2 to be a 2 to 3 ratio. So let's just test 2 to 3. And what I'm given here is a 5 to 6 ratio. So 2 to 3 is 0.67. 5 to 6 is 0.83. So see how this number is more than enough compared to this number? So what that tells me is I've got more than enough aluminum. So probably chlorine is going to be my limiting reactant. And I'm going to have extra aluminum left over. So that's what we'll practice tonight, is getting that limiting reactant. But the maximum number of moles that can be produced from 5 moles of Al and 6 moles of Cl2, because chlorine is my limiting reactant there, I have to go with the moles of chlorine. This is the one I'm going to have to use. So 3 moles of chlorine gives me 2 moles of AlCl3. 6 moles of chlorine should give me... Any guess? Which one, the limiting reactant or... Here, let me erase. So how did I... So I know that I need... In order to react, excuse me, to react 2 moles of aluminum, I need 3 moles of chlorine. So, in other words, let's do it the other way. Let's do 3 over 2. In other words, I need 1.5 moles of chlorine for every 1 mole of aluminum. So here, I would need, this moles of chlorine needs to be 1.5 times 5. So when I divide it, 6 divided by 5, what is 6 divided by 5? It's at 1 point. $1.6 or 1.2? Oh yeah, I should have known that. 1.2. So that's not enough, right? I need 1.5 times chlorine, but I only have 1.2 times the amount of chlorine. So that's why chlorine is the one that's the limiting reactant. And that's the one we're going to do the problem with. So 3 moles of chlorine yields 2 moles of this stuff. So 6 moles of chlorine yields 4. You got it.